In this video, we're going to talk about modeling with linear functions. To be more precise, we're going to try to answer the question, how can linear functions be used to model or describe real-life situations? Indeed, mathematics isn't merely an abstract pursuit, it was developed in part to help us understand the world around us. And linear functions in particular have many applications. Recall that a linear function can always take the general form f of x equals ax plus b. Here a is the slope of the function and b is the y-intercept. And one important thing to keep in mind when using linear functions to model real-life phenomena is that both of those constants tend to have a key real-life interpretation. The slope of a linear function can be interpreted as a rate of change. And in fact, linear functions are characterized by the fact that they have a constant slope or a constant rate of change. The y-intercept, on the other hand, is the initial value, which makes sense because it's simply the value of the linear function at x equals 0. With those ideas in mind, let's take a look at our first example problem, which is given to us as a word problem. It says that at time t equals 0, a car is 40 miles east of small town. If the car is driving east at 60 miles per hour, then how far east of small town will it be at time t? Let's try to break things down. Here, small town and the car are both marked on a number line, where we're taking right to be the direction east. And what's shown here is that at some particular moment, which we're calling time t equals 0, the car is 40 miles east of small town. We also know, however, that the car is traveling at a constant rate of 60 miles per hour. That means that for every hour that goes by, the car will travel 60 miles. And for every t hours that go by, the car will travel 60 times t miles. Just think of the formula distance equals rate times time. And this tells us that if we want to understand how far to the east of small town the car is at a given moment of time, well, we just need to add 60t and 40 together. And that will, in fact, give us the form of a linear function. Let's call it d of t. We can imagine that d stands for distance. And it will be equal exactly to 60t plus 40. And notice that, indeed, the number 60 in front of the variable t represents precisely a rate of change, right? It's the rate of change of distance with respect to time of the car, 60 miles per hour. And likewise, the number 40 can be interpreted as an initial value. It's how far east the car was from small town initially, that is to say, at time t equals 0. Finally, notice how the units of this problem function exactly as we would expect. The number 60 has units miles per hour, and the variable t has units of hours. And when we multiply them together, the hours cancel out, leaving us with just miles. And that miles plus the 40 miles still leaves us with units of miles, which of course makes sense because this function is intended to represent distance. Let's now turn to a second example that will also involve linear modeling. Suppose that in the year 2016, there were 500 freshmen at a particular high school, City High School, and that in 2019, there were 650 freshmen. This question will have two parts, and part A is asking us the following. If enrollment at City High School is growing linearly, then what is the rate of growth? To help us understand this problem, let's take a look at a pair of coordinate axes, where the horizontal axis measures years and the vertical axis measures freshman students. And notice that these axes have been tinkered with a little bit. These squiggles that you see near the origin are intended to indicate that we've sort of compressed the axis down, since the starting numbers on both the vertical and horizontal axis are rather large. The key thing to realize with this problem is that the problem statement is actually giving us a couple of data points, which we can plot on our pair of coordinate axes. Indeed, the problem is telling us that in the year 2016, there were 500 freshmen enrolled at City High School. So we can mark that point on our coordinate plane. The problem also tells us that in 2019 there were 650 freshmen. That, once again, is a pair of numbers that we can plot in our coordinate plane. And to understand the rate of growth, how many freshmen are arriving per unit of time, we of course want to compute the slope between these 2 points. And that's a rather straightforward computation. We will take the change in output, 650 minus 500, and divide it by the change in input, 2019 minus 2016. That simplifies to 150 over 3, or just 50. And this immediately gives us the answer to part A of the problem. The rate of growth is exactly 50 freshmen per year. And notice how those units make sense given how we computed them. And notice once again that the number 50 here represents a rate of change and therefore just the slope of a linear function. Now, here's part B of the same problem. How many freshmen will be at City High School in the year 2025? What we'd like to do next is construct a linear model that will do some work for us and give us information about freshman enrollment at a year that differs from any of the years specified in the problem statement. So geometrically, the situation is as follows. We want to take those 2 data points that we were given and then remember that a linear function is uniquely determined by 2 points that lie on its graph. So we'll construct a linear function that passes through our 2 data points, and then we should be able to use that function to determine what freshman enrollment will be in the year 2025. To write down that linear function, let's call it f of t, it's helpful to use the point-slope form of a line. Indeed, we've already worked out what the slope of the line is, right? That's 50 freshmen per year. And we have a pair of points that lie on the line, so we can simply choose one of them, like the point 2016, 500, and substitute it into the point-slope form of a line. This gives us our desired linear model, and all we have to do to finish the problem is substitute the year 2025 in for t, at which point a simple computation gives us an output of 950. Therefore, we would say that in the year 2025, freshman enrollment will be 950 students. And that, of course, is our answer to part B. Now, can we be certain that in the year 2025 there will be 950 freshmen at City High? No, of course not. It's important to keep in mind that our linear function is just a model. It will agree with reality in some respects, but it will likely disagree with reality in others. It predicts, for instance, that 100 years after 2016, freshman enrollment will be well beyond 5,000, which is probably unrealistic. However, when used properly, this model can still be very useful. Let's take a look at one final example. Suppose that you'd like to rent a car, and there are 2 companies that you can choose to go with. Company A charges a fee of $25 plus 80 cents per mile, whereas Company B charges a flat fee of $40 plus 50 cents per mile. Which company will give you the better deal? To help us understand what's going on here, it's helpful to model the cost of going with Company A using a function, and it will turn out to be a linear function. If x denotes the number of miles that you will drive the rental car, then the cost of renting a car from Company A will be 0.8 times x plus 25. Indeed, that number 80 represents a rate of change, right, cents per mile, and the number 25 represents the initial amount that you have to pay. It's that flat fee of $25. Likewise, the cost of renting a car from Company B will be modeled by a different linear function, the linear function 0.5 times x plus 40. Now, as you may have guessed, the question of determining which of the 2 companies gives you a better deal is a bit of a loaded question. Indeed, if we graph the cost functions for Company A and Company B, then we'll see 2 intersecting lines, which indicates that sometimes Company A is a better deal and sometimes Company B is a better deal. To understand exactly when that happens, we want to take our 2 linear cost functions and set them equal to each other. The result is a linear equation which, when solved, gives us a value of x equals 50. Which means that our two cost functions intersect at precisely the point where x equals 50, where the corresponding cost happens to be 65. So the interpretation here is as follows. If you plan on going on a short trip that doesn't exceed 50 miles, then you want to go with company A, because in between 0 and 50, the cost of company A is less than the cost of company B. On the other hand, if you plan on taking a longer trip that exceeds 50 miles, then company B will be the cheaper option, because when x is greater than 50, the cost of going with company B is less than the cost of going with company A.